Dear students, so in this class, let us discuss about a new chapter which is called algebraic numbers. We already know that. What's an algebraic number? Algebraic number means a complex number alpha is an algebraic number when it is algebraic over Q, means set of rationals. That is, alpha satisfies a non-zero polynomial, the polynomial with the coefficients in Q. Alpha is said to be algebraic, means it satisfies a non-zero polynomial whose coefficients are in Q. So if we clear in the denominators, then the coefficients may be present in set of integers, or the coefficients are integers. Okay. Now we prove a theorem. Let A be the set of all algebraic numbers, then this A be a subfield of the complex field C. How to prove this one? So its proof depends upon the well-known research. We know that when alpha is algebraic over Q, then degree of Q alpha over Q should be finite. That's a necessary and sufficient result arguments. That is, if alpha is algebraic over Q, then degree of Q alpha over Q is finite, and vice versa. So let alpha and beta are algebraic. Then we have degree of Q alpha beta over Q is nothing but degree of Q alpha beta over Q alpha into degree of Q alpha over Q. But alpha is algebraic over Q, then come to this one, degree of Q alpha over Q, that is finite. But what is beta? Beta is algebraic. Beta is algebraic over Q means beta is algebraic over Q alpha also. Our choice is alpha and beta are algebraic over Q. Since alpha is algebraic over Q, degree of Q alpha over Q is finite. Again, beta is algebraic over Q, so beta is also algebraic over Q alpha. When therefore degree of Q alpha beta over Q alpha is finite. So the two terms on the right side should be finite, means its product is finite. Therefore degree of Q alpha beta over Q is also finite. Okay. Therefore, also let under alpha plus beta, alpha minus beta, and alpha beta, where beta differs from 0, that should be present in where Q of alpha beta. That means this alpha plus beta, alpha minus beta, and alpha by beta are algebraic numbers. So all of these elements should be present in where A. Why? Because A be the set of all algebraic numbers. Therefore, A be a subfield of this complex field C. Okay, that is what we require. So the result, the proof is immediately followed from this well-known result. That is, when alpha is algebraic over Q, then degree of Q alpha over Q is finite. Clear? Yes. Now, come to a definition. That is, a number field K. K is any number field. Instead of this complex field comes this K be a number field. Then a number field K is a subfield of C. If K is a subfield of the complex field C, such that then degree of K over Q should be finite. Any number field K. A number field K is a subfield such that degree of K over Q is finite. That is, every element of K is algebraic, and hence K is a subfield of the all field A. So A is a part of, but we know that A be a subfield of C, hence K be a subfield of C itself. Okay. Now there is another result. That is, the theorem states that if K be a number field, we defined as when K be a number field, then it's a subfield of C such that degree of K over Q is finite. Okay. Now the theorem states that let K be a number field. K be a number field. K be a number field. Then K equals Q theta. then k equals q theta. What is theta? Where for some algebraic number theta is nothing but an algebraic number. That is what we requires here. So the statement is when k be a number field, then k equals q theta, where theta is any algebraic number. How to prove this one? So the proof is done by induction. So it is enough to show that k equals k1 alpha beta. K be a number field, then k equals q theta for any algebraic number theta. So by induction, it is enough to show that if k equals k1 alpha beta, proof. If k equals k1 alpha beta, then k equals k1 theta. Then k equals k1 theta, where theta is an algebraic number and for some theta, and k1 be a subfield of k. Okay. So forward, let p and q. Let p and q be the minimal polynomials. They are the minimal polynomials. Let p and q are the minimal polynomials of alpha beta. Polynomials of alpha beta over k1 means p be a minimal polynomial of alpha over k1 and q be a minimal polynomial of beta over k1. So suppose our C, we can factorize it as, suppose p of t equals, p be a minimal polynomial of alpha over k1. So let p of t equals t minus alpha 1 into t minus alpha 2 into etc. into t minus alpha n. Okay. And q of t. Q of t equals some t minus beta 1 into t minus beta 2 into etc. into t minus beta n. Here, where alpha 1 equals alpha and beta 1 equals beta. That's only for sake of situation. Let alpha 1 equals alpha and beta 1 equals beta. Also, all of these alpha i's and beta j's are distinct. That is, alpha I differs from alpha j, alpha I differs from alpha j, for all I differs from j, and beta s differs from beta r, for all s differs from r. Okay, so all of these alpha i's and beta j's are distinct. Agree. So hence for each I and k, for each I and k differs from 1, by alpha 1 equals alpha and beta 1 equals beta. So for each I and k differs from 1, there exists at least one element x following k. There exists at most one element, not at least, at most one element c following k, or x following k. At most one element x following k, such that alpha I plus x beta k equals alpha I plus x beta k equals alpha 1 plus x beta 1. There exists at most one element x following k such that alpha I plus x beta k equals alpha 1 plus x beta 1. If not, what happens? Why this is so? If possible, suppose there exists at most. How to prove this at most? If possible, suppose alpha I plus x beta k equals alpha 1 plus x beta 1. Okay, and alpha I plus x1 beta k, alpha I plus x1, if x1 beta k equals alpha 1 plus x1 beta 1. We prove that we have to show that there exists at most one element x1. How to prove this one? If possible, there exist two elements, x and x1, which satisfies this condition. Alpha I plus x beta k is alpha 1 plus x beta 1, and alpha I plus x1 beta k is alpha 1 plus x1 beta 1. What happens? So on the subtraction, what do you get? X minus x1 into beta k. If you subtracting vertically, so x minus x1 into beta k equals, on right side it is x minus x1 into beta 1. Okay. Yes. But what is x and x1? They are differs. X and x1s are differs. There exists, we have to show that there exists at most one element. We choose, if possible, there exists two of the elements x and x1. They are differs. So you can cancel in this x minus x1 on both sides. What do you get? So beta 1 equals beta k. That's a contradiction to the choice of this beta i's are distinct. Therefore, we know that, according to these arguments, there exists at most one element x fall in k such that alpha I plus x beta k equals alpha 1 plus x beta 1. Agreed? Okay. Since there are only finitely many elements, such as equations, we may choose some c differs from 0. There are finitely many such equations. We choose c differs from 0 in k1 not equal to any of these x's, and then alpha I plus c beta k instead of x. Alpha I plus c beta k equals, differs from alpha 1 plus c beta 1. There exists only one such equation. There exists at most one element x satisfies this condition. Alpha I plus x beta k equals alpha 1 plus x beta 1. Therefore, there exists only finitely many such equations. We may choose c differs from 0 in k1 such that alpha I plus c beta k differs from alpha 1 plus c beta 1. Why? There exists only one x satisfies this condition. So there exist finitely many equations which are not equals. Okay, where I ranges from 1 to n and k ranges from 1 to m. Why? Because alpha ranges from alpha 1, alpha 2, alpha n, and betas are beta 1, etc. beta n. So here for I ranges from 1 to n and k ranges from 1 to m, alpha I plus c beta k differs from alpha 1 plus c beta 1. Okay, so define, let theta equals alpha plus c beta. Let theta equals alpha plus c beta. Okay. Now there is a claim. What is the claim? The claim is k1 or k theta. K theta equals k1 alpha beta. This is our claim. K theta equals k1 alpha beta. How to justify this one? So we have, what is theta? Theta fall in where theta is an algebraic number. So theta fall in k1 theta. Theta fall in k1 theta. Okay. And also theta is defined as, or theta is taken as alpha plus c beta. So alpha plus c beta. Alpha plus c beta fall in where? Alpha plus c beta fall in k1 alpha beta. Okay. Theta fall in k1 theta. What is k1 theta? K1 theta equals k. Clear? Okay. So since theta fall in k1 theta, but also theta is in terms of alpha and beta, so alpha plus c beta fall in k1 alpha beta. So clearly from here k1 theta is a part of k1 alpha beta. So in order to prove this equality, first we show this first inequality, that is k1 theta is also a part of k1 alpha beta. Okay, so the claim is k theta equals k1 alpha beta. Since theta is in k1 theta and alpha plus c beta also fall in k1 alpha beta, therefore clearly theta alpha plus A beta is nothing but theta, hence K1 theta is a part of K1 alpha beta. So this is equation 1. Okay. What about the reverse inequality? So again, now we have theta equals alpha plus theta equals alpha plus C beta. Theta equals alpha plus C beta. That's our choice. So what is alpha? From here, what is alpha? Alpha equals theta minus C beta. Clear? Okay. So what about instead of t? What is P of theta minus C beta? P of theta minus C beta is P of alpha. What is P of t? T minus alpha 1 etc. But alpha 1 is, here we choose alpha 1 equals alpha and beta 1 equals beta. Okay. So what is P of alpha? P of alpha equals 0. Why? P of alpha is t minus alpha 1 means t minus alpha. Instead of t alpha, so alpha minus alpha, the first term is vanishes. So P of theta minus C beta equals 0. Clear? Now define a polynomial. Now we try to define a polynomial gamma t or rt, whatever. Define another polynomial rt, where rt equals r of t equals P of theta minus ct. That rt equals P of theta minus ct. Then we define another polynomial rt equals P of theta minus ct. So this P of theta minus ct, this should be present in where? K1 theta t. Okay. P of theta, P theta following K1 theta. So P of theta minus ct following K1 theta. Now come to this qt. Q of t equals t minus beta 1, t minus beta 2 etc. But we choose beta 1 is beta. Okay. So Q of t is t minus beta into t minus beta 2 into etc. So what is Q of beta there? Q of beta equals also 0. Sure. Q of beta is 0. Means beta is a 0 of this Q of t. It's a solution. Again, beta is a solution of this R of t. Why? What is R of t? P of theta minus ct. So when t is replaced by theta, t is replaced by beta, what you get? What is R of t? Here R of beta equals P of theta minus C beta. Okay, what is theta minus C beta? That is alpha. That means P of alpha. What is the P of alpha? P of alpha is 0. So we know that Q of beta equals 0 and R of beta is also 0. Q of beta equals 0 and R of beta is also 0. Okay, that means beta is a 0 of both the Q of t and the R of t. Beta is a polynomial, so beta is a 0 of both the Q of t and the R of t. Agreed? Yes. Now, so these polynomials Q of t and R of t has only one common 0. That's beta. How to prove that one? We prove that if Q of theta equals we prove that this Q of t and R of t has only one common 0. That is what we actually requires. How to prove this one? If possible, Q of theta equals 0 and R of theta equals 0. If possible, Q of theta equals 0 and R of theta equals 0. That means theta is one of this beta 1, beta 2 etc. beta. By Q of beta equals 0 and R of beta equals 0. When Q theta and R theta is 0, theta is one of this B1, beta 1, beta 2 etc. beta m. Also theta minus C theta is one of alpha 1 etc. alpha n. Why? Because theta minus c beta is alpha. Therefore theta minus c theta is alpha 1 alpha 2 etc. alpha n. Okay. If possible, if theta equals beta k, theta is one of this beta 1, beta 2 etc. beta n, and theta minus c theta is one of alpha 1 etc. alpha n, that is some alpha s. So if theta is beta k and theta minus c theta is alpha s, here means theta minus c into what is theta? Beta k. Beta k equals alpha. Theta minus c beta k equals alpha s. That means what is theta? Theta equals alpha s plus c beta k. Okay, theta s plus alpha s plus c beta k. But what is theta? But we know that theta equals alpha plus c beta. This is our choice. So on comparing, we have alpha s equals alpha and beta k equals beta. That means beta k equals beta. So that means beta equals theta. Okay. Yes. So that means this q of t and r of t has only one common zero. So that is beta. Now let h t be a minimal polynomial of, let h of t be a minimal polynomial of beta over k1 beta. Since q be the minimal, what is q? Q be the minimal polynomial of beta over k1. Okay. Now we assume let h of t be a minimal polynomial. Let h of t be a minimal polynomial of beta over k1. That means this h of t must divides q of t. Why? Since h of t be a minimal polynomial of beta over k1, and we assume that h of t be a minimal polynomial, let h of t be a minimal polynomial of beta over k1, and q be a minimal polynomial of beta over k1, then this h t must divides q. H t must divides q of t. That means this h of t must divides r of t. Okay. Yes. So, but q and r has just one common zero. Therefore, degree of h is 1. Degree of h equals 1 means what is h of t? So it is h of t equals some t plus mu. Okay. So degree of h equals 1. So h t equals t plus mu. So where mu fall in k1 theta. But what is h beta? H beta equals 0. H beta equals 0 means what is h beta from here? What is h beta? H beta equals 0. H beta equals 0 means t plus beta, beta plus mu. So h t equals beta plus mu.